Thanks for coming, Ron. My pleasure this morning to introduce Tom Botterill-James. Tom's actually a postdoc with us here at UC and working in collaboration with myself and Dave Forsyth at New South Wales IAE and colleagues down at the University of Tasmania. But we don't see too much of Tom because he's based down in Tasmania, so it's been a real pleasure to have him here this week. An opportunity to meet others in the Institute tonight. So Tom is from Tasmania. He did his undergrad and PhD there, and I think he did his PhD in behavioural ecology. But in the last couple of years, he's kind of switched tack a little bit and moved into looking a lot at modelling spatial dynamics. And he's going to be, I think, telling us about the work that he's done with Barry Brook in his lab around biodiversity and land use change, and he's going to talk a bit about the work he's doing with Dave, myself, and other colleagues on deer in Tasmania. So thanks very much, Tom.
Yeah, thanks, Richard. Yeah, should be. Yeah, sweet. Yeah, thanks for the intro, Richard, and thanks everyone to come and listen. It's really truly a two-part talk today. Yeah, talking about the stuff I've done in Tasmania over the last couple of years, and then more recently, the last few months, yeah, here at UC with Richard and Dave at New South Wales DPI. Yeah, I'll get stuck in, do the acknowledgements for all the clever people who contributed to all this, all the institutions providing funding. It's always a fun part of a talk, sort of doing a quick and dirty image search at all your collaborators and seeing what pops up. Yeah, Richard doing a Jim Morrison impersonation there. Cal and Chris with taxidermy animals, Barry in a leather jacket, and then Dave's the only professional kind of in there. And yeah, as Richard kind of alluded to, kind of traditionally a behavioural ecologist, I guess. Someone knows me here from Tassie, so I can't take credit for these cartoons. Yeah, I kind of did my PhD looking at sort of family dynamics, particularly focusing on lizards. I did all the natural history kind of stuff, sort of harassing animals in their burrows and taking measurements and sticking things on them. Sort of doing the sort of binoculars, taking lots of notes. And yeah, then towards the end of my PhD, I was starting to get, found out lots of interesting things, but also kind of, everything kind of had a postdoc explanation on it. Maybe it's a species specific or, something happened in the environment this year to produce this result. I started getting a bit hungry and sort of looking at some sort of broader scale methods to try and answer bigger picture questions. Yeah. The last talk I gave was like a science outreach, so it's just going to be full of memes and stuff, I think. And yeah, so that segues nicely into this first part of my talk, where I sort of focused on really using meta-analysis as a tool to quantify how biodiversity responds to land use change, looking at Southeast Asia as a region. And then I'll talk a little bit more about some simple models that I use to predict what might happen to biodiversity in the future from land use change. So kind of one of the motivating factors for focusing on this region is that it's sort of over the last few decades had some really high levels of land use change, so highest in the world in terms of deforestation through the 90s and 2000s. It's just sort of in green, you see all this historical forest cover, and then particularly in black, you see that you're getting that replaced over time, particularly by plantations. So things like oil palm plantations, rubber plantations, hardwood plantations. And lots of people have tried to kind of quantify land use change effects on biodiversity with like really, really broad kind of studies, looking at it from a planetary scale, but really biodiversity kind of might respond to land use changes differently within kind of different ecoregions, right? And you might miss kind of variation in the sensitivity of different taxa to different types of land use change if you kind of zoom out too much. And, kind of motivating factor, that final thing that kind of led us to do a meta-analysis on this was that there's lots of primary data out there on how biodiversity kind of responds in different kind of land use classes in Southeast Asia, but no one's kind of done the work to pull it all together and try and synthesize it. So yeah, just a little bit of a kind of just meta-analysis 101 for, I'm guessing some of you might have done this technique before or read about it and others haven't, but essentially what it is it's just a statistical method for kind of combining studies together from a related kind of topic and then getting a statistical output. So example here, we've got our 5 studies, A, B, C, D, and E. The circle represents the effect size from that study. And there's a uncertainty, that bar associated with the effect. And there's an overall effect, a statistical effect at the bottom of that clear diamond. And so it's kind of the nice thing about meta-analysis is if you're trying to do a vote count technique to kind of see what was happening on this topic, you go, oh, well, study A, we don't really know. It doesn't show an effect because there's too much uncertainty. Studies B and E, we see sort of differing effects. So you wouldn't really get a clear answer, but by kind of pulling them all together and incorporating the uncertainty associated with each study, you can kind of get a bit of an idea of what the effect size actually is. And this just shows another key kind of property of meta-analysis, which is that studies that are more precise are typically, better conducted and well replicated studies that have, a sort of tighter measure of uncertainty around their effect, have a greater weighting in your calculation of your overall effect size. So you see those bottom two studies really sort of draw the effect size towards them. And finally, we can kind of look at other covariates, just like any model, you can look at covariates that explain your effect size. So for my meta-analysis, you kind of see this slide for anyone who's ever done a lit review. I went through thousands of papers, and I really did. And sort of narrow that down to 830 effect sizes from 111 studies. And I kind of strict criteria on what would constitute an effect size. So the effect size here is basically a measurement of biodiversity in a control site, some sort of untouched forest that's had very, very minimal human disturbance that's been compared to another plot in a disturbed forest. And yeah, like I said, I had sort of key controls. So those control sites and disturbed sites have to be matched in terms of being a certain distance away and having other kind of key confounders like roads and stuff taken out of it, so that you're really drilling down on the effect of land use change on biodiversity rather than some other effect. So sort of went down the Bayesian path for this and used multi-level models because there was lots of non-independence in this data set. Often you have sort of multiple effect sizes coming from the same study. You even have the same kind of sample for each effect size. So you'll get different biodiversity metrics taken from the same set of animals or plants. So have to control for that non-independence by sort of using this multi-level hierarchical modeling. Use cross-validation to kind of pick apart a set of models that differed in their predicting variables, predictors of that magnitude of effect size. So I focused on just a simple kind of disturbance intensity. So when the intensity of the land use change was high, and that's where you might have sort of slash and burn agriculture, you get an area of forest replaced by a plantation of some sort, or you might have a sort of forest area replaced with an urbanized area, or low intensity, and that's sort of things like where you have agroforest systems. So you get these land use changes where you replace primary forest with agriculture, but they keep some remaining native vegetation in the habitat matrix. And finally, also compared between different models in terms of how I model the structure of between study variance. So by that I mean this sort of idea that in a meta-analysis, you're kind of pulling apples and oranges together and you want to quantify just how much variance there is overall in your study, in your data set. And typically what you do is you just estimate from study to study how much it varies, and then you get an overall kind of measure of heterogeneity between studies. But really, you might actually have heterogeneity sort of varying between subpopulations in your data set, right? So you might have some kind of groups that are more heterogeneous than others. And if you don't account for that, you miss out on a lot of noise, and you can cover up the effects of predictors of your effect size. And just a kind of little example of this that's not from my own work, but kind of look up here. This is a study where you looked at discrimination in hiring rates in different countries. So we got this, you guys see the laser pointer up there? Now, if you look at panel A, you look at all these effects that come from France, and they're really spread out when you look down compared to Germany. They're really tight. And so sort of ignoring plots B and C and jumping down to this plot D here, what you find is that if you estimate an overall effect size for each country without accounting for that sort of difference in total heterogeneity within each study, within each country, kind of mischaracterize the effect. So you kind of don't pick up an effect for France when you assume that there's a single amount of between study or between effect size variance for the whole data set. Whereas if you allow that to vary by subpopulations, you actually get to estimate the effect a lot better. So you pick up that effect more strongly. And this can also have effect with things. These are posterior distributions looking at the effect of a covariate, which I think was the amount of immigrants in each country, how that affects that effect size. And if you don't account for that sort of variable variance, if you like, you kind of miss out the effect of that covariate on the effect size. So back to my own stuff. These three different coloured posterior distributions represent different models I fit that either allowed the variance to vary between study to study or applied a global kind of average between study variance, or a model where I didn't have any kind of variance in there at all. And the dashed line represents the actual posterior distribution from the data. And all this kind of shows is that this middle distribution that fits the data really well, that's a model where I allowed the variance to be variable between each study, which is what you might expect, because ecological kind of studies can be super variable, right? So you want to allow flexible variance for effect sizes that come from different studies. And yeah, just to kind of show these other distributions, it kind of shows that if you don't model that variance appropriately, you might either sort of get too narrow of a confidence interval of the effect that you're looking at, or it might be too broad. So you might actually kind of miss out the effect because you've got too much uncertainty around the effect size you're trying to estimate. And yeah, so all this is to say is that sort of in meta-analysis, typically you focus on the mean, but if you also sort of try and focus on modeling the variance between effects a little bit more too, you can kind of drill down on your effects a lot better. So then moving from modeling those kind of different various structures to performing model selection on models that varied in the predicted covariates of effect size, that effect of how does land use change affect biodiversity. I fit 9 different models. So I fit a null model that had no predictors of the effect size, fit a model where you looked at whether metric explained the effect size. And so by metric, I mean, I'm sort of looking at what sort of measure of biodiversity the studies were looking at, whether it was sort of species richness, abundance of the species that were measured, or sometimes it was measures of forest structure, such as intactness or canopy cover. Taxon, so I just grouped this into 3 broad categories: invertebrates, vertebrates, and plants. So seeing if any of those taxa are more sensitive to land use change than others. And then disturbance intensity, like I said, so whether the intensity of land use change affects how biodiversity respond. And then I fit all those models in 2A combinations, all 3 of the predictors together, and then I finally fit a full model, which was all of those factors and their interactions combined. And what you can take away from this, I've highlighted this with the circle, is that the further to the left those dots are, that's better the predictive performance on the model using sort of cross-validation, and those error bars represent the uncertainty of that model's predictive performance. And so you see that kind of that taxon plus disturbance, metric plus disturbance, and those kind of more complicated models that have all of those factors in perform really well, they're predictive really well. But that model that has disturbance in as the sole predictor of effect size performs equally as well when you take into account the uncertainty. So you might say, well, if you were to just try to use this model as a pure predictive tool, maybe you chuck all these covariates in. But if we want to actually try and make some inferences about what's going on, we just kind of focus on that simpler model. And so this is kind of the nice big key graph from this paper. This represents each of these dots with those error bars represent an effect size from a study and the associated uncertainty with it under both cases where the land use change was low intensity and when it was high intensity. And just to kind of, rather than walk you through step by step, just to put the key message in that is that when you have low intensity land use changes, you get 18% less biodiversity compared to those control reference sites, primary forest sites. When it's high intensity, you get 35% less biodiversity. So yeah, really quite, it's not really ground baking, right? Like this is what you'd expect if you're going to do slash and burn agriculture versus kind of keeping a large amount of native vegetation. You're probably going to keep your species there, but it's kind of nice to put a figure on this for uncertainty. And then I kind of sort of post hoc ran some models to kind of drill down on some finer scale differences in how different types of land use categories might affect biodiversity. And kind of don't see any what we call statistically significant effects here, right? But kind of interesting just to look at what's happening, and you find that in these kind of agroforest plantations, you get a reduction of biodiversity, but it's not as great as what you get when you replace primary forest with oil palm plantations. And sort of looking at how biodiversity recovers in sort of plots that are allowed to recover over time. These three categories: young secondary forest is abandoned agriculture plots that have been allowed to regrow for up to 20 years. Intermediate secondary forest was, I think, 20 to 40 years of regrowth, and then mature secondary forest is forest where in the study they classified it as either being sort of a similar structure to primary forest or had been 40 plus years of recovery. And what it shows is that you sort of still have lower amounts of biodiversity in young secondary forest, but then once it kind of goes through that succession and recovers, 20 plus years, you have similar amounts of biodiversity to what you have in primary forest. So from there, I kind of got all these, I had heaps and heaps of data to kind of see what was happening with biodiversity in different types of land use change. I kind of wanted just to put some basic modeling in there just to kind of see, okay, what might this look like in the future if you get kind of different rates of land use change occurring for the region's biodiversity. So what I did was I took published models from the literature. I didn't do my own land use change modeling. I took sort of other people's estimates of what might happen to the future to 2100. And typically all these kind of land use change studies model land use change under different socioeconomic pathways, right? And sort of past approaches have kind of done a similar thing. They've tried to estimate what might happen to biodiversity in the future, but they've kind of relied on just extrapolating based on kind of observed deforestation rates, which you might expect kind of won't give you a good idea of what will happen into the future if you're kind of just assuming you're going to get a linear increase of deforestation and more forest is going to be lost. You might actually think, well, kind of over time, once you kind of hit a certain point, it's going to level off. And you might even get things like reforestation processes occurring. So those are the three socioeconomic pathways I chose to sort of pull from those studies because there's a bunch of them, but I thought I'll just sort of use three to contrast. So the sustainable pathway where you get kind of slowing down human growth, reduced amount of resource use per capita and in total, a kind of business as usual scenario. And then finally, a kind of intensified development scenario where you get increasing human population growth, increased per capita use of resources. And then kind of just use the good old species area relationship to predict sort of as you get a decreasing proportion of habitat or an increasing proportion of habitat, what kind of percentage of species might go from certain areas. And just on this, typically these kind of species area relationships, there's a parameter in there that kind of describes the affinity of species to different habitats. Or in this case, we're sort of describing a sensitivity of species to habitat loss. And because I've done that big meta-analysis, I actually kind of put numbers on what sort of amount of species you might lose under different types of land use change. And what I did was I just applied that parameter equally across all different taxonomic groups because I didn't find that was a predictor of how you get responses to land use change in my meta-analysis. There's lots of numbers on that plot. But basically, I just want to show that across all these different countries in Southeast Asia, for all countries under that, first that sustainability pathway scenario, if you just apply a rough species area model it actually predict that you get recovery of species because you get reforestation occurring across Southeast Asia. You get a similar kind of increase or recovery of species under a business as usual scenario. So I guess these models are kind of predicting that you're actually getting a shift in Southeast Asia where reforestation is occurring in that scenario too. But then if you have intensified development, it predicts that you're going to lose species. And the worst is, I think it was in Cambodia, it predicts you get about 4% of species might be lost by 2100. That's it, some for Southeast Asia. Its distributions look a little bit wonky. I don't know what's going on there, but anyway, it just shows for the whole region, that's kind of summing those results together. You get a gain of species or recovery when you have that sustainability pathway. You get a recovery of smaller magnitude when you just have a business as usual scenario playing out, and you get a loss of species when you get intensified development. And so, some caveats, that's just kind of really rough modeling, applying a species area relationship to these kind of like changes in forests that we're predicting, and sort of predicting that you're going to get species increasing in those regions by 2100 assumes that species that have been lost, that there's sort of small pockets of them that are going to be able to recolonize the area once you have reforestation occurring. And potentially, again, we're relying on, even though this kind of land use change modelling is a little bit more of a refined method than just extrapolating deforestation rates. They're also kind of forecasts, right? And there might be limits to the extent that Southeast Asia can reforest, given that sort of big sort of areas in Europe and North America where you've had that forest transition occur already. They kind of tend to displace their land use change to other regions. So there might be limits to the extent to which you actually see reforestation occurring in the region. Just to kind of summarize this part of the talk, land use change decreases biodiversity. The more intense land uses you have, the less biodiversity occurs, which is, I put the exclamation marks in there kind of ironically because that's exactly what you'd expect. But again, meta-analysis is a really nice tool if you collect enough studies and run a good model to get a good estimate of what that effect actually is with an uncertainty measure. Kind of some indications that biodiversity recovers quite nicely when abandoned agricultural areas are allowed to recover to a state that resembles the original forest structure. But again, that's sort of got a caveat on it that it's true in terms of the kind of metrics that we picked apart in this meta-analysis, like species richness and abundance, but for more kind of nuanced measures like the composition of species and the functional diversity of species, you don't know if you're actually going to recover that fully potentially. And then, just did some sort of basic scenario modeling to show what might happen into the future, and kind of shows that you might not actually necessarily kind of get these big doom and gloom scenarios that people are predicting if sort of really kind of moderate land use change scenarios are followed. So a bit of a shift of gear from that, that type of modelling, that sort of statistical modelling at a broad kind of regional level into what I've been working with the last few months with Richard here and Dave at New South Wales DPI. It's kind of doing some simulation modelling of the spread of invasive deer in Tasmania. And so when I talk about deer here, I'm talking about fallow deer. It's the only species of deer that you get in Tasmania, introduced to Australia in the 1800s. And sort of becoming a bit of a pest problem across different regions in the country due to the fact that they graze native vegetation, so impact on conservation values and also kind of have economic costs through their effect on crops. In Tasmania, they were introduced from England. Kind of as most sort of non-native things are, people bring all their favourite animals from home. And it was kind of initially a small population that was really constrained within the site of release over sort of 150 odd years. But then in the early 1970s, you had sort of 7,000 to 8,000 deer, in best estimate, occupying a really big area, potentially just from natural population growth and spread, but also because there were sort of ongoing releases and people farming deer that escaped. And a recent paper from collaborators on this project sort of shows that the population is on the up. So if you model the increase over the last few decades based on government spotlighting data, you kind of see that mean deer per transects kind of follows this exponential growth curve. If you look at the occurrence area in panel B, you can kind of see that's going up quite a bit too. And you're getting in this map, you're seeing the distributions getting bigger and bigger across time. And that's despite harvesting also increasing, which you can see in panel C. So those numbers, if you kind of want to put some numbers on it, it's about a 40-fold increase from 1985 to 2019 in population size, and a tripling of size in the modelled estimated core distribution. And that's the current estimated distribution based on a joint likelihood model of that spotlight data and camera trapping data sets. You can see they occupy quite a big amount of area in Tasmania now, so they're not just constrained with a 60 kind of kilometre home range. That translates to about 27% of Tasmania estimated as being occupied. And in terms of the total abundance, the recent government aerial survey kind of estimated that you've got 54,000 deer. And that's only in that kind of range here through the Midlands and northeast of Tasmania, not kind of accounting for these satellite populations that occur down south, up in the northwest, and these island populations too. So that estimate of 54,000 deer is a lower estimate. And kind of anecdotally in the 70s and 80s, deer weren't really much of a problem, but now you're kind of hearing lots and lots that they're coming into conflict with different sort of values. So one issue is that they're starting to collide with vehicles, so they pose a bit of a safety risk. The Tasmanian Farmers and Graziers Association estimate that they cost more than $10 million to farmers every year in terms of their impacts on crops. Greening Australia has been sort of running a big Midlands restoration program over the last few years, and they're spending a ton of money trying to fence deer out of those areas and sort of having to replant trees because deer come along and eat these kind of young tree growth. And then also you're seeing deer in kind of areas that are of really high conservation value. So there are lots of different issues that kind of means that we might want to start thinking about how to manage them. And just to add to this, there's also predicted to be more deer on the way. So if you look at the habitat suitability of these guys, across Tasmania, pretty much all the areas climatically suitable for them. That's based on, that climate's sort of based on their occurrences in their sort of more native range back in Europe, or where they're at equilibrium and not invading. In panel B, you've got their habitat suitability, and that's a little bit more constrained because deer don't quite like rugged terrain, whereas lots of Tasmania has quite rough terrain. And if you kind of fit those two maps to occurrences of deer based on a small sort of set of camera trapping data, you get this sort of selected, weighted, combined habitat suitability map in panel D. And if you binarize that map, you get panel E, and it shows that about 55% of Tasmania, I think, is suitable for deer to occupy. And given the current distributions, only 27% of Tasmania, there's obviously potential for them to spread even further than they are now. And a few years ago, some sort of basic modelling to look at sort of carrying capacity in similar environments and kind of predict what that might mean for Tasmania. But potentially, it can hold up to 1.4 million deer. So yeah, so this population has kind of been increasing the last few decades, and it looks like it can potentially increase more. So what to do about this problem? There's a need to predict where expansion and growth is more likely to occur. So we know that, if we don't do anything, they're going to keep spreading, but we want to look at maybe where are they going to spread into areas of conservation, where might we try and fence them out, say, or where might we harvest them to stop them getting into areas of concern. And peri-urban areas as well. So we want to keep them away from getting into urban centres where they might pose a risk to people driving cars. And finally, it'd be nice to estimate kind of how effective different control measures might be at achieving certain management goals. So we might kind of want to put some numbers on an upper limit or an upper spread that we want deer to kind of reach, and we can kind of measure the cost effectiveness of different ways to achieve that. And so a potential way to do this is to do some scenario modelling using a spatial population model. So this is what I've been developing over the last few months in conjunction with Richard and Dave. And this demographic model is sort of spatially explicit in terms of it's applied. You've got this demographic model, a age matrix applied to a 25 kilometre square grid. And yeah, the model contains information on vital rates, fecundity and survival, contains information on dispersal patterns of deer. It's seeded with the initial population from 1985. And we've got those habitat suitability maps in that I just showed you, and carrying capacity kind of estimated from what deer do in similar environments in the Northern Hemisphere. That all sounds well and good, but obviously there's lots of unknowns. So there's actually limited sort of hands-on ecological data for fallow deer in Tasmania. And so some of those parameters that I just described in the model, we don't really know how to estimate them well, other than kind of just picking out from the literature, kind of sort of guesstimates. So we don't know what the carrying capacity actually is for deer in the most ideal Tasmanian habitat. Don't really know how far they go, or what kind of dispersal patterns they really have. So it'd be ideal to kind of get values for these parameters that are sort of estimated in a more systematic and robust way than kind of just looking at the literature and trying to rationalize what other people have found and applying it to our own study system. So this is where kind of applying a pattern-oriented modelling approach. That's essentially, it's just a way, it's a sort of jargony term, but it's just a systematic data-oriented way of fitting spatial population models to real-world patterns to kind of estimate those parameters in your model. And so to do it, what you do is have that spatially explicit population model. You can simulate it over time, and then you can match your simulation results that you're hindcasting against independent real-world patterns that you know. And then by selecting only the subset of simulation models that replicate what you know actually occurs in reality, you can kind of estimate the parameters in those models. And if you run lots and lots of simulations, say thousands, right, and you pick a percentage of those models, you get a measure of uncertainty with your parameters as well. So you can kind of estimate mean values and uncertainty measures around those parameters. So it's kind of a neat way for kind of filling in these gaps, these unknown gaps in our model that we don't really know or would have to otherwise rely on kind of picking from the literature to try and fill. So just to illustrate that, for those of you who are visual learners, first step is to have your spatially explicit population model. That grid, essentially, you've got those values coloured according to habitat suitability. In this example, it's dynamic over time. In our model, it's just static because it's not over that much of a long time frame. You apply a demographic model, which has sort of information on survival and fecundity of individuals between age, or you can have it as a sort of stage-based matrix. And then in this sort of panel B, estimate parameter uncertainty. So this example, you've got carrying capacity on this y-axis, dispersal on the x-axis, and survival on the z-axis. And you use latent hypergrid sampling to sort of sample this big parameter space. And then you run simulations of models that contain all these different values of parameters. You project your spatial population model. And then in panel D, you match the outputs of the model. In this case, they're looking at extinction dynamics rather than invasion dynamics that we're looking at. But they've got validation targets, which is what time do you observe extinction. And that in panel E, you can kind of see that those subset of models that you select, you get an estimate of the mean parameter value, and you get a posterior distribution to show the uncertainty around that value. And then because you've done all this sort of nice simulation modeling, you've run lots of models, you've only selected a subset of models that replicate your known patterns in the world. You then have validated models that are parameterized that you can then run to either sort of run forecasts further into time, or you can sort of look at sort of the underlying dynamics that are fed into the model. So what do the parameters actually mean in terms of ecology or whatever you want to look at? It's a bit of a text-heavy slide. Essentially, our spatial population model for deer in Tasmania, has an age-structured sort of demographic matrix in there. There's stochasticity applied in the matrix. It's made spatially explicit by applying it to a grid of habitat suitability across Tasmania. And then we've got a bunch of other parameters in there, and including at each time step, well, not at each time step, but at certain time steps, we can add in populations where we know that there's been deliberate translocations or escapes of deer from farm. So to parameterize the model, to find those parameters, we generated 20,000 samples, and the samples for each parameter are just sort of drawn from a uniform posterior distribution. But this kind of framework you can specify, you know, if you kind of have prior knowledge about the parameters you're trying to estimate, you can kind of draw it from a normal distribution or something a bit sort of more informative than just a uniform distribution. And the sample parameters that kind of the key ones we looked at were functions or components relating to dispersal. Because like I said, no one's actually gone out and GPS collared deer down in Tasmania. So we're really stabbing at the dark, trying to understand how far and you know, how many individuals in each cell might disperse. So that was one of our sample parameters. The maximum carrying capacity of deer in the most suitable Tasmanian habitat. That was another estimated parameter because, you know, you look at the literature, you sort of try and figure out a value for this based on similar environments in the range with their equilibrium back in Europe, and there's, you know, lots of different values. So rather than kind of, I don't know, just picking a centered value or you know, trying to average out a value, you can sample it using this pattern-oriented approach to dial in the parameter. For custody and survival, sort of tweak that by having a multiplicative factor in the model between 0.9 and 1.1. So the population growth is looking a bit slow or it's going too fast, depending on the validation targets. That kind of, by modifying fecundity and survival, you can kind of get the slope of the population growth a bit more dialed in. There's also sample parameters relating to harvesting. So to validate those models, we use 2019 distribution of deer estimated from that joint likelihood model of spotlight and camera tracking data. That's what that looks like. And we also used statewide abundance estimate from 2019. So we set that conservatively at 60,000 deer based on the fact that you find 54,000 in that core range, but they're at really high densities. If you run all those simulations, kind of plot it. So that's that kind of distributional target. So the number of correctly predicted cells as being occupied or not is on the y-axis. And then on the x-axis, that's that final abundance metric. So all these black dots are the results from all those simulations. That's the best 200 models out of those 20,000, and the actual target is sort of in there somewhere. So you can see, you kind of sample that parameter space quite well, and you can replicate the targets quite well. And from that, here's just an example of two of those parameters that we estimated. You can kind of see the proportion of animals that are dispersing. I have this uniform prior that we put into the model, but then when you try and run the simulations and match your simulations to your target, you actually get this posterior is sort of centered down this way, and you get quite a nice estimate. So that's a parameter where we've really identified we need to kind of shift it. Then looking at the sort of average distance that deer disperse, you actually see that the posterior distribution that we estimate's not too different from the prior that entered the model. So that might suggest as well we kind of need to think a little bit more about, you know, maybe trying to trying to dial in that parameter if we're sampling and it says, well, we don't really know what the actual value is. So just to look at how that model performs, if you want to try and predict the distribution over time using the validated model, so the model that contains sort of that mean parameter estimate for each of those sampled parameters. Those layers just represent different times. So layer 1 is the deer distribution in 1985. Layer 2 is distribution, I think, in 1995. This is the distribution in 2005. That's that final distribution in 2019. You can see the validated model does quite well at replicating the spread of distribution. So particularly this kind of final distribution step, you're getting that core range replicated well, but the nice thing is to see that you're getting these seeded populations, these satellite populations away from the main range sort of persisting in the model. So it does quite a good job of simulating that known pattern. And then sort of still working on actually dialing this in to run some forecasts, but just as an example, if you use that validated model and then you actually, instead of just replicating it back in time to kind of recreate those dynamics and you want to look at what might happen, running it to 2050, this is the final distribution that we get from that validated model. So you see, you know, those kind of satellite populations really grow in size and the abundance keeps going up. It starts to level off by 2050 at 250,000 animals. And so obviously, you know, kind of demonstrates that it's kind of useful just to get some potential scenarios that might occur in the future. And so that model that I showed you, there's still sort of work to do to tweak it in to kind of really get it sort of matching those known patterns a little bit better. So I only got 2 validation targets in there, and you know, you might think, well, maybe we can add some more data that we actually know about to try and validate the model even more and get it representing reality as best we can. And so that's kind of the next steps I'm looking at. So rather than just having a final distribution and abundance target, one thing that we could potentially do is we've got this spotlighting data from the government that has time series of sort of mean deer per spotlight transect over time for different regions. So potentially we can try and see how the model fits to that sort of mean deer detections over time. So fit a time series to try and get the model validated. We can also validate it against this model distribution as well. And finally, you know, it'd be nice to sort of, rather than just forecast and show what might happen, we might also want to try and put some inputs into a forecast model to understand what the effects of different control measures might be. So here's just a little table just to illustrate some of the kind of scenarios that we're planning on looking at. So ground shooting using just recreational hunters. You have ground shooting by professional hunters. Things like aerial shooting. There's other potential control measures like fencing that we can look at too, because there's data available on how much these things cost. If you kind of, you know, model sort of simulate these in that forecast model and then apply the costs to it, you can kind of get an idea of what might be a cost-effective strategy for trying to achieve certain management goals. I guess just to kind of wrap that up, I guess a good takeaway from this kind of pattern-oriented modeling that I've kind of sort of taken away sort of doing it is that, you know, it's a really nice technique, but it's definitely very dependent on the actual data that you have. So, you know, you can build these nice spatial population models and you can validate it, but the validation of the model and the model that you produce is only going to be good if you have good data to try and test it against. And so, you know, that's kind of what I was saying at the end there. Just putting in as much data as we can to try and fit the model to is going to get the most useful model for then doing those kind of really interesting things where we want to look at mechanisms underlying sort of dynamics of spread and growth and sort of estimating the effects of interventions. Yeah, thanks for listening. Take some questions if you have any.
Thanks for a nice presentation. I've got a question. It's something around when you did that in your model that you basically you showed that it was able to predict the invasion of one of the islands. And how is that in the model? Because you can't have something they go.
Yeah. So there's a translocation function in the model, and so essentially we do have some data from the game services unit down in Tasmania where they go, oh, we know that this population was released, at roughly this time, and so where we have good data on where they've been released at a certain time step in the model, we'll see the population, which again, it's kind of a So it's not quite a real magical emergent property. It's a little bit driven by what we've done. Yeah.
First, what would your suggestion be to the Southeast Asian countries? What pathways forest restoration? So, and secondly, what's the
Yeah. Yeah. I'll answer the second question first. So there's actually a feasibility study done like a year or two ago, commissioned by the government to kind of look at what's the feasibility of using wild shot deer, as a kind of commercial product, because it'd be great, right, if you can sort of have a population control measure for invasive and also have it generating some money, and it can be an incentive to have recreational hunters. Or landowners who are sort of protecting their crops kind of go out and get these deer, but you get a lot of backlash. I think there's, I think there is a bit of appetite, but there's also just as much backlash from people who have commercial deer farms saying, oh, if you use wild shot venison, it's gonna stuff our business up. So I think the feasibility study where it's at is because there's a management plan for fallow deer now, just released a couple of months ago, Tasmania, and they've got a few they're sort of relaxing some different sort of tagging requirements and permits for hunting deer. And they're sort of saying that once they've looked at the effect of the management plan in 4 or 5 years, I think it's maybe 5 years, that they'll kind of assess whether can sort of go back to that and look again at using wild shot deer as venison. I think they're also sort of looking at maybe potentially using it for pet food too, which might sort of go through a bit quicker potentially. And then, the question for what do you do if you're a Southeast Asian country trying to balance land use change against biodiversity loss is a hard one. Like all the literature for that's kind of, people like all those primary studies, right, measuring biodiversity in primary forests and then different types of land use change. So you read so much about oil palm plantations being particularly bad, and I guess it's a big one in the media, like oil palm's terrible for orangutans and whatever. But if you actually look at sort of the amount of like the yield per amount of land that you get from oil palm plantations, like they produce a lot of product for the actual amount of space that you use. So I don't know, I think that's kind of the sort of next interesting step in that kind of modeling, is kind of actually doing some more sort of like, sort of yield versus biodiversity trade-off. Kind of get at that a little bit better, I reckon.
I want to ask about the supplementation. And that's in terms of when you look at how loss of biodiversity might change depending on things like climate, where a place is dry, places warmer, like that. If you look at it,
So no, but I did look at whether it was different between sort of ecoregions. It's kind of one of the hard things with these meta-analyses is like how much do you aggregate your data to kind of get sort of big samples to look at these kind of things versus, plugging in lots of really interesting kind of covariates that might explain the effect and then kind of losing a bit of power. Kind of just looked at whether, because, you kind of have these distinct regions in Southeast Asia, right, where you might expect it will be different on the mainland, you know, through Thailand and Vietnam versus some of the archipelago regions. And so sort of splitting up by ecoregion and having a bit of a sort of just look at it, there wasn't much of a difference. Sort of qualitatively, it's sort of worse in the Philippines than anywhere else, but you know, it's kind of like, so once you start aggregating that data, the sort of sample sizes drop and you get big uncertainty around the effects that you're estimating. So it's kind of hard to say too much about it. Yeah.
So I suppose it means that it's like a stick.
Yeah, yeah.
It may be, you know, 100 kilometers away, but dispersal, where, you know,
Yeah.
Did you consider that at all? That sort of aspect?
Yeah, that's kind of, so in that kind of manuscript, it's kind of making that point that, yeah, you don't really, you know, at the very least, we're kind of saying maybe under those scenarios, you won't get further loss of biodiversity, and these kind of recoveries, you know, you're probably not going to get those sort of that extent of recovery because, yeah, things that might be locally extinct, and it is going to be hard for them. You know, some things might not even exist in an area where they can disperse back, but kind of interesting to think about potentially, you know, translocations to certain areas might be feasible in the future. But yeah, it's kind of really dependent on actually having existing sort of populations that are able to disperse back in, which, you know, for most cases, probably not going to be true.
You might check the chat for questions.
Oh, yeah.
What Tom says, is there anyone?
It's so long.
Yeah.
I think I know how to do this.
You know, you've got any other questions? Here we go.
Oh, beauty.
Okay, all right. We might leave it at that then. Just to say that I think Dave and I are going to go for lunch with Tom. If anyone would like to join us after this. But meanwhile, thanks very much, Tom. Lovely to have you here for the week.